So, second problem seems like it's basically a repeat of the first one, but there's a little extra oomph to it because you get through the first two strategies that I showed you, and then you realize that it's not taking you in the right direction. You're like, oh, well, what do I do now? But you got to start somewhere. So what we do again is we hold one of the variables constant. Now, something to keep in mind, you can hold the variable to be constant at whatever you want. I mean, I can let x equal 20 if I want. It just wouldn't serve any purpose. But x is a variable. If I want it to be constant, all I have to do is make it not vary, right? But the most logical thing to let it be equal to would be 0, because that's what we're approaching. So hold x constant at 0. And again, you do enough of these examples, you stop wanting to write hold x constant at 0 repeatedly, so it becomes let x equal 0. But you got to understand that what we're doing is we're creating a pathway, a plane that will intersect the surface, which will create a pathway that you can travel along. It's a cross section, all right? It's kind of like if there's a hill or a mountainous region, and you were to create a cross section of it, you'd be slicing a plane right through that, vertically, right through that region. What it traces out along the circumference, the edges of the hill, the highest points, lowest points, the peaks and valleys and all that, that is the pathway that we're looking at, right? And all we want to know is where this is going as we follow that pathway, all right? Is it going to Mordor or is it going somewhere else, right? So I'm going to write the limit as y approaches 0 because all of my x's are getting replaced with zeros. So 0 times y over 0 squared plus y squared. Now that just boils down to just 0. 0 over anything is going to be 0 as long as that anything isn't 0 itself. All right? Because this is really the same. I'll show the intermediate step now that I think about it. Limit as y approaches 0 of 0 over y squared. And that 0 over y squared simplifies down to just 0, and the limit of a constant is a constant. All right, so we have a value to compare with, all right? There are no wasted steps in this. So we held x constant at 0, and you're like, I got x equals 0. I need to show that the limit does not exist. You're not going to get just a d and e, right? You got to get a limit from one pathway in order to show that a limit from another pathway is going to give you something else, all right? So now I'm going to hold y constant at 0. And that's going to give me the limit as x approaches 0 because x still varies. Y is the thing that's constant. So y times 0 over x squared plus 0 squared. All right, so just like the previous one, that's going to be the limit as x approaches 0 of 0 over x squared, which is the limit as x approaches 0 of 0, which is 0. All right. Now, again, no wasted steps, but you look at this and say, well, that sure seems like a wasted step. We're trying to show that the limit does not exist. This seems like we're showing that the limit does exist. All right. But what we're getting from this is from two different pathways, the y value is approaching 0. All right. Now, the graph, I mean, what are you getting from the graph? It's so iffy. I can't tell if this is a smooth curve that's coming down. It seems like it is over here, or is this going to be kind of like a cusp, all right, where it comes up and then it has a steep drop off. It pitches back in where you have no points that exist in that empty space. I can't tell, all right? So I need something else, all right? So this is where things get interesting. I can let x or y be anything I want, all right? I could even let x and y be some kind of relationship with one another. If we go back to the first page, think it was, yeah, it was number 2 on page 51. The one that said 9 minus x squared minus y squared. What we got for that domain was that x and y could be anything as long as the relationship was that x squared plus y squared was less than 9. All right? That's going to come back into play repeatedly over and over again throughout this unit. And that is, yeah, okay, well maybe y and x aren't constant values. Maybe there's some relationship between x and y, right? Maybe the pathway that I'm taking is not a plane. Maybe it's a parabola. It's parabolic, right? So imagine a parabola with height. It'd be some sort of bowed figure. So you'd be looking at something that looks like this. Right? This is a parabola with some height. Right? It could be like that. All right? Maybe it's a cubic function. All right? This is what a cubic function in 3 space would look like. All right? It's just basically a cubic graph, just with some depth to it. All right? I don't think I can do a trig. Oh, I could do a trig function. Here's a sine function. All right? You could, like, any number of possibilities come into play. All we're looking for is some kind of relationship between x and y. I just need a pathway that's going to get me to that location, but then also give me a limit that's something other than 0. All right, so we'll start off with a linear relationship. Maybe it's along the path where x is equal to y. I'll write y equals x. All right, so it's another plane. I need that plane to go through the x, y value of 0, 0. All right, so thinking back to just 2-dimensional space, that would be the origin. All right, forget about z for a second. I need some relationship that allows x and y to both, like the x and y values to both be equal to 0. Y equals x, x equals y works. All right. So what I do at this point is I replace one of the variables with the other. All right. What a lot of people will do is create what we call a dummy variable to replace both of them. Because if x and y are the same, then I could just say, well, let's let t be equal to x and y. All right. So that's what I'm going to do because it keeps things a little cleaner. So let my dummy variable t equal x and y. And so I'd redefine my limit in terms of t. So instead of x comma y approaches 0, 0, since t is taking the place of x and y, t would approach 0. And so I'd be looking at t times t over t squared plus t squared. So I'd end up with t squared over 2t squared. And like I said, this is a personal preference. I mean, a lot of other people have the same personal preference, so I guess it's really not too personal. But you could just, I mean, if x and y are the same, you could use direct substitution and just replace all your x's with y's, or replace all your y's with x's. All right? So you'd have the same expression, perhaps, but just with x squared over 2x squared as x approaches 0, or the same thing but with y's. It's all amounting to the same thing. But the great news is the t squares will cancel away. And the limit of a constant is equal to a constant. And that constant 1/2 is not the same as the other constants of 0. So therefore, the limit does not exist. So the big question I usually get at this point, not that I want to preempt any of the questions that you might have, but how do I know y equals x? Well, I started simple. I started with x being equal to a constant, y being equal to a constant. I could have tried a different constant. I don't know how that would have played out. But then I start escalating my function, right? So constant functions are power of 0. The next one up would be linear. Then after, if this didn't work, I would try quadratic. Maybe I'd let y equal x squared. If that didn't work, y equal x cubed. X to the 4th, x to the 5th. if the polynomials weren't working, maybe I try a trig function, all right? Just a note on that, I would never try a trig function unless I looked at the graph. And for these kind of questions, I give the graph because I want you to be able to evaluate what's going on. Even though you're not going to be able to look at the graph and say, oh, clearly the limit does not exist, you should be able to look at it and say, a trig function is appropriate or a trig function is not appropriate, right? This one looks like maybe there's a little oscillation going on there. Maybe a trig function would be appropriate. So maybe instead of going along the path y equals x, maybe I go along the path of y equals the sine of x. All right, so that's another pathway that's open to you. All right, so what I'm going to do, well, you know what I'm going to do. I'm going to put a star on that one because I'm exercising my teacherly right. I mentioned last time, oh, packet. So, yeah, you know what you're up against. You know that the limit's not supposed to exist. It's just a question of making that happen, which can be, in a lot of cases, more frustrating than actually not knowing what the limit's supposed to be. Because, you know, you could stare at a problem for a while and think to yourself, well, I just showed 17 different ways in which the limit does exist, but the problem's saying that the limit does not exist. So is there a typo? What's going on here? You know, but in this case, we're looking at something that really does not exist. So, but we're going to approach it the same way we did all the other questions, and that is by first just plugging in the value and seeing what happens. If I do that, though, I'm going to get 0 over 0, which is indeterminate. All right. So that didn't really tell me much of anything. So what I'm going to do is hold one of the variables constant. So I'm going to hold x constant at 0. All right, so y is the only thing that's going to vary. So I'm going to redefine my limit in terms of y. So y approaches 0. I'm going to replace all my x's with 0. And that's going to 0 out the top and leave me with just a y to the 4th on the bottom, which simplifies. You know, I'm not even applying the limit. All right, we simplify this. 0 divided by anything is going to be equal to 0. So limit as y approaches 0 of that constant 0 would result in a 0. All right, so that's the first challenge. Now, it's a good outcome because in order to get a limit that does not exist, we have to first get a limit that does exist from one pathway, right? So now what we want to do is try to show that the limit from a different pathway is going to not exist. All right, so what I'll do now is hold y constant at 0. So I'd be looking for the limit as x approaches 0. Still going to 0 out on the top, but this time over x squared. Simplify, we get the limit as x approaches 0 of the constant 0, and that's going to be equal to 0. All right, so no help there. All right, we're looking for a limit that's going to be different from the ones that we got. So now I kind of extend my thinking to account for other types of functions. All right, so we could try what we did in the last problem. Maybe we're following the path y equals x. All right, so let's do that.
If x equal to y or y?
No, same.
Oh.
So what I'll do is I'll follow the path y equals x. And if that doesn't work, I'll try y equals x squared. If that doesn't work, I'll try y equals x cubed. If that doesn't work, maybe I'll switch over and try a log or a trig function. One of these is going to work though. Generally though, the types of functions are going to be specific to what you see in the expression. So I'm probably not going to incorporate a trig function if there is no trig in the original expression. I'm probably not going to incorporate an exponential or a log unless there's an exponential or a log in the original function, right? So following the path of y equals x, what I'm going to do is let y equal x equal some variable t. And I'm going to redefine my entire limit in terms of that new variable t. So limit as t approaches 0, because both x and y are approaching 0, and t is replacing x and y, so t, if it's approaching 0, it accomplishes the same thing. Replace every x with a t and every y with a t. So cleaning it up, I get t cubed over t squared plus t to the fourth. Now, if I apply direct substitution, I can probably move on from this, but, you know, because it's going to be indeterminate. But, you know, you look at it, you say, well, there's a common t squared I could factor out and cancel, so let me just do that. So t over 1 plus t squared. All right. So if I, in the previous step, replaced all the t's with zeros, I would have got 0 over 0 and moved on to a different path. But if I simplify it, I can substitute in and get 0 over 1, which is 0. So after all that, it was of absolutely no help. So I got to try a different path. So follow the path. And you can see how I'm increasing the order of the pathway. All right, I'm starting off with a constant function. You know, when I'm saying hold y constant at 0, I'm really saying follow the path y equals 0. Right, linear equation. All right, constant linear equation. And follow the path y equals x. So I'm incorporating a variable x to the first power. So x to the 0th power, first power, second power. Maybe we'll try third power if this doesn't work. But then after that, I'm going to say, wait a minute, I might be taking the wrong approach. Right? Now, the graph can be a useful thing, and I'll explain to you what I mean by that in a minute. Sometimes you can kind of glean from the graph some useful piece of information that kind of allows you to streamline the approach. So if I let x equal t, then based off of this relationship, y would have to be equal to t squared. All right. Now, another possibility because I chose a parabolic pathway. Who's to say it's y equals x squared? Maybe it's x equals y squared. If that's the case, then I would let y equal t, and x would be equal to t squared. So I'm going to do both of these simultaneously. And you'll see that one of them is going to get you in the right direction. And I'll show you how you could streamline it in a second. Streamline it a lot, because there's a lot here that doesn't need to be here. So t is going to approach 0, because whether x is equal to t or y is equal to t squared, if x is approaching 0 or y is approaching 0, it's still a case where t is approaching 0. All right. In my first case, I'm gonna replace all the x's with t's and all the y's with t squares. So t times t squared squared over t squared plus t squared to the fourth. Or, if I went the other way, and have the limit as t approaches 0 of t squared times t squared over t squared squared plus t to the fourth. All right, so that's all direct substitution. So I'll clean them both up. Limit as t approaches 0. I'm going to have t to the fifth on top, t squared plus t to the eighth. Simplify. You get t cubed over 1 plus t to the sixth. And when you plug in, you get 0 again. You're like, no. But then for the other way, you're like, oh, that work. Something magical happens. Math magical. You get t to the fourth over t to the fourth plus t to the fourth, which is the same if I divide everything by t to the fourth, 1 over 1 plus 1, which is the limit as t approaches 0 of 1/2, which is 1/2. Therefore, the limit does not exist because at long last, we finally got a limit that's not the same as all the other limits. All right, because we kept getting the 0, but we needed something other than 0. All right, so again, you're dying to know how we can streamline this significantly, and I'm going to tell you that in a sec. Because there are at least 3 or 4 calculations that did not need to happen, but we had to go through it this one time in order to see that it didn't need to happen, because I remember I was a student in class. I don't like it when this happens, and I see it in textbooks all the time, and it's almost like, and you've witnessed it. You definitely witnessed it, whether you realize it or not. The teacher throws a fact up on the board, and is like, okay, and so t is equal to 20, and then they just kind of move on without really explaining it, and you're questioning, well, where did you get that from? It's almost like they pulled it out of thin air, and I can tell you, even from personal experience, that's the teacher trying to sneak one by you, because they didn't really want to explain where that number came from, because it's probably too challenging to explain it. So they're like, let me see if I can just throw this up there and then move on without anybody noticing. All right, that's this concept. Because if I were to do that, it would be like, all right, how'd you know? And I'd be like, well, you just got to look at it. You know, it's not good. All right, so the shortcut. What you want to do is come up with a pathway that would allow your denominators to have the same power. All right, so that's the big challenge here. All right, so I want to define a t value that allows the x squared to have a power of 4. All right, so if that's the case, then what I would need to do is make x equal to t squared and y equal to t. All right, so if x is equal to t squared and y is equal to t, I have it written here, so I guess I don't need to write it down again, but if I make x equal to t squared, that would make this t to the 4th. If I make that y equal to just a t, then that makes that t to the 4th, and the sum of which will give us a single term with that common power of 4. The idea is that we had 2 separate terms, and when they were separated out, they were causing all the problems. But if I can combine them together, that could be the recipe for cleaning it up, all right? And so this goes all the way back to parametric equations. Once I decide that x has to be t squared and y has to be t, then I could come up with a pathway just by substituting, right? Because if y is equal to t and x is equal to t squared, then x has to be equal to y squared, all right? So that gets you your two-dimensional pathway to lead you, well, essentially where you want to go. So that's one way you could figure it out. The other way, or another way, it's kind of unfortunate, but it relies on you being able to look at a picture. And we know that that could be a problem. Okay? So three-dimensional graph, if you have GeoGebra, if you have GeoGebra AR, okay, cool. I'm sure you could do something with that. When you have one of these printed in grayscale on a handout, that's not quite as nice. But the key really has everything to do with the wireframe of the graph. So don't get so much into like the shading of it. Just look at the wireframe of it, right? So in that wireframe, you should be able to pull out a distinct function of some kind, all right? So follow the wireframe, and let me make that a little thicker. A lot thicker, actually. And if you follow that wireframe, you see that it's a function that has a dip in the middle and then comes back up. All right, and you can see that that happens in a few different places, just in you know different ways. I'll put arrows on it. So this seems to be upward parabolic. I mean, it's even more pronounced as you get closer to the middle. Upward parabolic, downward parabolic. All right, just based off of the wireframe. Now, the trickiest aspect of that is you can look at that and say, yeah, I see that it has a dip and it has a curve in it. I'm not thinking parabola when I see that. I'm thinking cosine. But my advice to you is to start simple. All right? You're not going to start off with like an inverse cosecant function if you can actually start off with just a y equals x squared or x equals y squared. All right? So it has a little belly to it that resembles a parabola. So that's your indicator that, okay, it's probably not a linear path that's going to get you there. It's probably going to be something that's curved in some capacity. Now, if you can actually look and see what's going on around the origin, because that's what's happening, then it usually becomes even clearer. All right, so right around the origin, it's definitely hard to see in this case, but this looks like a parabolic pathway on one end, and then on the other end, also parabolic. All right, so if you're just focusing at or in the region surrounding the points of interest, then you can usually pull it out there. The one drawback is because this is a three-dimensional figure, you can only really discern what's happening in the cross-section that's perpendicular to your line of sight. Right? So as you're looking at it perpendicular to that, that's really all you can pull out of it. Right? It's harder to see what's happening in a straight line, like the depth into the paper, what's really going on there. That's why it's so blurry in here, because there's a lot of other movement that's going on by points around that region that you can't, that like the computer is confused in how to render that in a two-dimensional graph, right? But as long as you can pull out from this a function, a reasonable function, then you got what you need, right? Me personally, I look at this and I say, well, it's not linear, right? That's one thing I got, right? I didn't get much more than that, but I know it's not linear. So what does that tell me? It tells me that I'm going to still do one of these calculations because I want to have something to compare all my other limits to. So I do this one, skip that. This is linear, skip that, jump right to parabolic. All right? And if that doesn't work, then I'll try cubic, then I'll try something else. All right? And again, if there's no log in your expression, there's no reason to incorporate an exponential at all.
on number 2. How would you?
So this one, I mean, it's definitely harder to see, but around these points here, it actually is somewhat linear, right? But because the key is you're looking around the points, all right? You may not even get the linear part of it, but the odd function nature of it is what you should really come up with. So just following this curve here, this wireframe, we have for points surrounding 0, you can make a case for linear. All right, so what I would say in this regard is if that didn't work, if I tried linear, I wouldn't even bother with quadratic, because if I follow this wireframe, I can see that it's extending outward, and it's not in a parabolic fashion. This looks more like a cubic. All right, so if my linear case didn't actually work, then I would go for cubic or any other type of odd function. And generally that's going to play out. All right, so if I tried this, you know, like replacing x with t cubed, you know, that's going to scale up, but, you know, maybe there's some other y that'll allow me to combine the two. All right, so, and in fact, I think if you do x cubed equals y cubed, that would get the job done. It's just, it would simplify right down to y equals x, so it would still do the same thing. All right. But yeah, this area over here is a big old mess, so you can't really tell, so you always default to the wireframes. And if we could look over the hump, you would be able to see that there's another wireframe on the other side that also has a linear aspect. I'm kind of exaggerating it because it's actually over the hump, but there's another linear looking aspect of it just on the other side of this hump. All right. Of this, right, from Calc 1. Maybe from Calc 1. This is one of the most popular topics that are skipped in Calc 1 when people run out of time. Yeah. Depends on what time of year you take Calc 1. If you take it during the summer, it's definitely skipped. If you take it during the spring, it may or may not be skipped depending on whether or not there's a lot of snow. Okay, so, but usually it's one of the first topics to go. Okay, but it's not bad. I mean, don't get me wrong, that makes it look like it's bad. This is very frightening. But really what we're trying to do is find the limit of two functions that we know surround the given function, right? X squared y over x squared plus y squared. All right, so I want to designate two functions that I know surround that function. All right, find the limit of those two outer functions. If I find that limit and it turns out that they're equal, or those limits, and it turns out that they're equal to one another, then the inner function, the one that's trapped in between those two outer functions, would have to take on that same limit. All right. So you know what? Let me just go back and Calc 1 it real quick. So I'll give you a quick Calc 1 example. Because honestly, I mean, you're just going to be memorizing steps. If you've never seen this in Calc 1, that's all you're going to end up doing if I don't show you this. So let's say you have a limit as x approaches. Now I got to remember the example. Do I want infinity? I'll go with infinity. Keep it simple. Something that we know we could find the limit of, you know, whether you know it off the top of your head or you just know how you would find it in the calculator. This is something that you could easily find the limit of. All right. So what I want to do is determine a function that I know, or a pair of functions that I know surround this function. All right. So 1 over x plus 1, I know that that is going to be in between two other functions. just a question of what those two functions are. All right. Now we could look at this numerically, but we could also, I don't know, we could look at it graphically. We could look at it just logically. Let's just take a case, a numerical case. Let's say I have the number 1/2. All right. The number 1/2 and the number 1/3. I'll write the number 1/3 here. What's the relationship between these two values? Greater than, less than, or equal. What do I put in between? Well, I don't put an equal. Is 1/3 bigger than or smaller than 1/2? Smaller. All right. So this is smaller than that. All right. So if the denominator of a fraction is larger, then that fraction's value is going to be smaller than the other fraction. All right. So what I would want to do is come up with a fraction that I know definitely is going to be larger than this. In order to do that, I just need to come up with a fraction that I know has a denominator that's smaller. All right. So 1/x will get the job done. Generally something simpler. That's kind of the point. All right. So let's take a look at the graph real quick. All right. So yeah, let's just take a look. Not too dissimilar to something I was working on before, apparently. So 1/x plus 1. So I'll just do a little alpha fraction, 1/x plus 1. And then 1/x. Taking a quick look at the picture of my terrible scale, so I'm just going to bring it in a lot. All right. Now this is going out to infinity, so I only care about positive values. Let me just bring it back. The graphs, let's see. It's hard to see on that, but the 1/x is the red one. All right, so 1/x is the red one. Can I make that a little bolder? Yeah, definitely. Ooh, that's too bold. Good enough. All right, so this is my 1/, of course I got my color scheme backwards, but this is the y equals 1/x, and this is y equals 1/x plus 1. All right, so it's pretty clear that this is a function that's all, or maybe it's not clear, but it seems as though that this function is always going to be physically larger than this one in terms of y. All right, so now I just need something that's going to surround it on the low side. Now, all I have to do is reflect y equals 1/x over the x-axis. And I'll get something that's going to naturally bound it on the low side. So it's going to look something like this. All right, so it'll naturally bound it on the low side. Both are going to have the same horizontal asymptote. So they're going to converge for extreme values of x. And this function y equals 1/x plus 1 is always going to be trapped in between. All right, so if I could figure out the limit as x approaches infinity of these two outer functions, then I'll have the limit that I'm looking for. So what I do, and it's just a simple notation trick here, is I apply the limit to each element of the inequality. All right, so on the low end, I'm just looking for the limit as x approaches infinity of -1 over infinity. That's going to be equal to 0. And on the high end, same deal. Now you may be wondering about my magical transition from less than symbols to less than or equal to symbols. That's less magic than it is theoretical. The idea is that this limit is talking about getting out to infinity. If I were ever able to actually get out to infinity, all three of these curves would have merged into the same curve, right? So they would have equality. But it isn't until I apply the limit that less than becomes less than or equal to. But this is a proof, this is a squeeze theorem proof for the limit as x approaches infinity of 1 over x plus 1 being equal to 0. That's Calc 1, all right? Whether you saw it or not is a different story, but, you know, should have seen it. Or maybe not. I go back and forth on that. I don't know, like, because what's the point of seeing it in Calc 1 if the next time you're going to see it is now? I don't know. Either way. But anyway, we have to apply that now. But fortunately, we're using the same thing.
Squeeze theorem because the lines are squeezed into it.
Exactly. Another name for it is the Sandwich Theorem, but that just sounds absurd. Squeeze theorem is borderline what we're willing to accept in terms of like non-mathematical terms to justify something, but calling it a sandwich theorem, I'd call it a hoagie theorem or something. Like this is like if we're gonna go nuts, we might as well go nuts. So what we're gonna do here is we're gonna start off with a relationship that we know to be true, all right? Like for example, I know, and I'm just gonna start with the denominator because that numerator is a little funky. I'm just gonna start off with that denominator, 1 over x squared plus y squared. I know that that's gonna be less than 1 over x squared. Or 1 over y squared, just not both. Right? My rationale on that is the denominator is smaller for the larger fraction. Right? So it's a true statement. Now, we may end up spinning our wheels here. We go through the whole process and find out that I chose poorly and go back and choose 1 over y squared instead. But the bottom line is my second fraction needs to be larger than my first fraction. In order for that to happen, its denominator has to be smaller than the first fraction's denominator. All right? So if I reflect this, I get negative 1 over x squared. Now, my middle function is not 1 over x squared plus y squared, it's x squared y over x squared plus y squared. So what I can do is multiply the whole shabiggity bang here by x squared y. And when I do that, I'm going to get negative y is less than x squared y over x squared plus y squared, which is less than, in turn, less than y itself. So in the previous, or the example that I created, and by the way, if anybody's looking for typo bonus, that example, that could be an example that I use for future classes. I might as well just throw it in there. It seems like a reasonable use of our time. So the typo could be on page, whatever this is, include Calc 1 squeeze theorem example. All right, and I'll know what that means. I don't generally like to get in the habit of looking at everybody's grades throughout a class session, but for typos, I don't think there's too many people. Yeah, there's only two instances where somebody has submitted a typo throughout the whole course. Right? Was that? Not that I know of. I think somebody might have beat you out.
Early on.
Yeah. So all you have to do is on remind, just page number, what the error is and what the fix is. Do that for 3 separate instances and you get 3 bonus points. All right? It's pretty easy because as you've seen, I make typos all the time. Right? And spacing is the #1 thing. Like if I could fix one thing about my notes moving forward, it would be spacing. All right? So like for those instances where like I gave you 1/4 of an inch of space to do like a 1.5 miles worth of work, like tell me about those instances because that's going to make my life easier. Because again, we know this. I'll never run out of space, right? So, but you repeatedly run out of space. So anyway, I'm going to apply the limit as xy approaches 0, 0. As we go forward, you're going to find that that's probably the most annoying part of this, having to write that repeatedly, which is why I use the squiggly bracket notation instead of writing it for each part. Right? And you'll see here that for the outer functions, the x part is irrelevant, right? Because it's kind of like we're holding holding x constant. It just kind of worked out that way. So I'm replacing y with 0 on the low and upper bounds. I'm getting 0, and so I'm looking at the limit as xy approaches 0, 0 of that given function is in between 0 and 0. So it's a pretty safe bet that it's going to itself be equal to 0 by the squeeze theorem. All right? And by safe bet, I mean it's guaranteed. I want to be absolutely clear about that. There will definitely be a squeeze theorem problem on the next unit test. The good news about it is there's only so many of them that work. So what you see is what you get. Like what's going to be on the test related to the squeeze theorem is going to look an awful lot like one of these. All right? Maybe it won't be x squared y over x squared plus y squared. Maybe it's x cubed y over x cubed plus y cubed. But it's going to be structured almost identically to one of these problems. All right, so an opportunity for you. Now, number 5 looks really, really complicated in comparison. But I'll tell you right now, it's no more difficult than number 4. All right, it just has a lot of extra oomph to it. It looks a little crazier, but it's not at all any more difficult. All right. The one thing you do have to be mindful of, these are approaching, xy is approaching 0, 0. Now it's approaching 1, 0. Right? So people who mess this up, they mess it up because they get in the habit of putting zeros in for both x and y. All right? You got to actually see what the limit is approaching. All right. Huh. No, okay. I was wondering why I put this here, but this is actually the appropriate placement for it. So we're looking for continuity. In order to address continuity, we have to determine the domain. All right. So looking at this function, I want to identify any instance where the denominator would be equal to 0. That would happen if x squared minus y is equal to 0. All right, so my domain is going to be related to this equation, which can be simplified a little bit, really just by adding the y to both sides, y equals x squared. All right, so my domain specifically in the appropriate notation is going to be that x and y are my variables, and my restriction is that y has to be the squared values of x. Whatever x is, square it, that's going to be equal to y, that's going to be the restriction to this function. So what I did was I actually graphed on GeoGebra the original function and then the restriction, all right? So in order for this graph to exist, every x and y value has to follow this pathway. All right, so for continuity, because continuity and differentiability are still going to be a thing. So it's a question of, well, where does the function exist? Where does it not exist? So when it comes to making a determination of when a function does not exist, this relationship comes into play. All right, it goes back to what we were talking about with vector values, vector valued functions. The function has to exist at certain points, and then the limit from all directions need to exist. All right. So what that's telling me is that I need to show, or at least have a reason to think, that the limit. Now, we don't have enough information to continue with this one, but at least we could talk about the setup. We need to state that the limit as xy approaches AB of x squared minus y is going to be equal to really the same function, just with a's and b's in it. All right, so it's really just direct substitution, which is it's not difficult. So we would just say a over a squared minus b. All right, but again, as long as we know that where b is equal to a squared, as long as we know that b is equal to a squared, we're going to be in good shape. All right. So one thing that you could do is actually replace certain values. So for example, this is more kind of an analytic approach. It's more of a proof than anything else. You're not really establishing anything in the realm of, I don't even know what the right word is, like finite math, but you can at least progress a little bit.
So isn't that just
A over 0.
is a squared is b?
Oh,
Shouldn't it be y can't be x?
yeah. It's one of those days. So then, yeah, because what I was about to do was, actually, yeah, okay, so there actually is something you can do, because what we can show or prove the limit does not exist when y equals x squared. I mean, there's really not much you can do with that, I don't think, but it's something. Without any numbers in the problem, there's really not much. But if I were to say, instead of the limit as xy approaches AB, I could say the limit as x comma x squared approaches AB. And then replace all my y's with x squares. I would get the limit as x comma x squared approaches AB. This looks terrible. See, like I said before, you find as you go forward that the most aggravating part about any of this is writing what the limit is approaching, especially if it's in 3 variables. So you end up with x over 0, which is undefined. And so we would say the limit does not exist. But that's really all you could do. I mean, it's significant though, but I don't think it advances the plot too much, because we already knew that. Like, this is just saying what we knew by setting this equal to 0. So it's really more of a valuable situation when you're given particular numbers. But it was something. So why not? So, we did that one. Yeah, yeah. Oh, I didn't scroll up. Huh. I thought this was the only problem on the page. Very good, thank you. Let me sit down. Standing too much recently. Back for taking a beating. All right, so prove that the limit exists and equals 0. So another squeeze theorem problem. But basically, it's all coming down to whatever you see on the bottom of the fraction. So I'm just going to write the denominator, 1 over x squared, x minus 1 squared plus y squared. Now, I want to create an inequality out of that. All right, so what I want to do is I want to make a statement that that's going to be less than 1 over x minus 1 squared. All right, because smaller denominator means larger fraction. All right, so this is a true statement. I don't even have to know what x and y are in order to know that this is true, because I know that y squared is guaranteed to be a positive number, because anytime you square a number it's positive, and I'm adding it to something else that I know is positive. So whatever that first fraction is, it has to by definition be larger than my second fraction, 1 over x minus 1 squared. All right, we also learned last time that if we reflect that function over the x-axis, aka negate it, we get a function on the other side that when coupled with that first function, so let me highlight them, these two functions together will eventually, for extreme values of x, squeeze together to trap that middle function, that middle expression, as you go out towards infinity. All right, so the idea is that if I could find the limit of the two outer functions, if they turn out to be the same, then they will have squeezed together, they will have merged, and then whatever is in between those two functions would have to also merge. All right, the only thing is, this middle part of the inequality isn't what the limit question is asking about. So I just have to make a couple of adjustments, and then I'll be able to apply my limit. All right. First, I got to multiply through with that numerator, the x minus 1 squared natural log of x. The second thing is more like, I don't want to say it's intuitive, but it's more like just being aware, because there is a natural log, which means that there are domain considerations. But as it turns out in this case, they're irrelevant, because natural log has a domain where the x values have to be non-negative. I'm sorry, positive. They have to be greater than 0, right? So since I'm going out to infinity, let me just double check that. Oh no, I'm going out to 1, 0. All right, so that's something I definitely want to be careful about. But since x has to be greater than 0 for the natural log, it's fine, because x is approaching a value that's greater than 0 anyway. All right. But it is something that you should be aware of, because it could impact things. You know, because if a question said find the limit as x, y approached negative 1, 0, then it would be a DNE right off the bat, because the function wouldn't exist at that location. All right. Of course, the question wouldn't say prove the following limit exists and is equal to 0. It would say what is the limit. So this one's actually going to be pretty easy. It's just you got to write a bunch of things, and that part is kind of annoying. I mean, more than kind of. It just is what it is. But you know, at first glance, you look at it and say, well, I don't see how this situation is improved at all. But you can see here that we have a common x minus 1 squared. Those are going to cancel away. So it's my middle expression. Negative ln of x is less than that middle expression. Which in turn is less than the positive natural log of x. And now I'm at the point where I can apply my limit. So squiggly brackets. All right, so natural log of x, when I go to find that limit, well, it's only the x value of the ordered pair that's relevant. Right? Because x, y is going to 1, 0, but this doesn't have a y, so there's nothing to substitute in for y. So I just have to plug in the 1. Right? Well, what's the natural log of 1? Speak. 0. It's nice when that works. Doesn't always work, but sometimes it does. All right, so yeah, natural log of 1 is equal to 0. So my two outer functions have limits that are going to 0, which means that the middle function must also take on that same limit. So this one just seems a lot harder because you just got to write a lot more, but conceptually it's no more challenging than the other stuff. It's just when you get to this step and you realize what the answer is, just knowing that you got to write limit as x, y approaches 1, 0 of all this crap again, it's just like, ugh, do I really got to do that? And then you got some schmo like me waiting to take off points for you accidentally rewriting something incorrectly. I don't really go looking for that. If it's obvious, then I have to take off credit, but this is, in most cases, kind of a rubber stamp when it comes to grading, because generally, most people have the process. And so it's just a matter of just me eyeballing it and making sure that all the bits and pieces are generally in the right place and you have the right answer. Yeah. And you know what the answer is supposed to be going into the problem. So you're generally going to be in good shape. One drawback to something like a question like this is, previously for limit questions, there was a calculator technique that you could fall back on, at least to get the answer going in. For these kind of questions, I mean, it's a function of two variables. So you really can't. It's not like you can type it in the calculator and see what the limit's going to be before you even get started. So you're relying on me giving you some information going in of what you're looking for. Right? And generally that's the way of it. I'm not going to say find the limit. What I'm going to say is prove the limit does not exist, prove the limit exists. If I'm feeling very generous, prove the limit exists and is equal to something. But at a minimum, I'll give you prove the limit does not exist or prove the limit does exist. Right? So at least you know that you're supposed to go in and either not get an answer or get an answer, something specific. Right? That's very mathy looking. It's kind of nice. All right, so the last thing we're going to talk about tonight are partial derivatives. And I'm going to let you off the hook. Well, I'll be honest. I'm going to let myself off the hook and not get into the limit definition of a partial derivative, because really it's the same as the limit definition of a derivative. You're just going to have y's in there when you're taking the derivative with respect to x, and the other way around when you're taking the derivative with respect to y. It's really just kind of aggravating, especially since it's something that you would already have a pretty decent sense of. Now we will get into the graphical representation of this stuff because there is a lot of meaning to it, because we're taking a partial derivative. So what is that, like a quarter of a derivative? What are we talking about here? Is it like a little piece of a derivative? What's going on? So we do have to get into like why on earth would this be a useful thing to learn about. But for now, with the last few minutes that we have, we're just going to get into the act of taking derivatives. And also what are known as second order partials. All right, the notation, it looks pretty similar to the ordinary notation for derivatives. It's just the lowercase delta symbol is actually what we use for partial derivatives. Right? Now, it's kind of interesting to think about this, but I don't know if you ever got the origin story behind the notation in Calc 1. When you learned about dy dx, and I'll just actually do that real quick, because I think it's valuable for people to know this, because some of the notation seems like it comes out of thin air, but it really doesn't. So you have slope, general slope formula, delta y over delta x. right? That's capital delta. And I'll highlight it. Got to move slightly and then highlight it for some reason. All right. Now, that slope is specifically over an interval. All right. So slope over an interval. I always saw calculus as being an entire set of course. Well, it depends on the course, but Calc 1, I say it's an entire course dedicated to the study of slope. And I don't think I'm lying. I think that's actually what it is. All right? It's just what are you doing with those slopes. Then you have slope at a point. All right? And so for that, we use delta y over delta x. All right? Also delta, but this time it's a lowercase delta. All right? So what happened is in Calc 1, they kind of streamlined that down to just d, with the reason being, I'm not going to write that symbol over and over again. That seems like a waste of effort. So we'll just use d. The reality is, even in Calc 1, you are working with partial derivatives because every first single variable, I almost said first order function, single variable function can also be thought of as a multivariable function, but with one of the variables being held constant. All right, so when you're taking the derivative of y in terms of x, you are taking the partial derivative of the function y in terms of x. It's just you're holding y constant.
Does that mean we can just use a d here? Oh, lowercase d.
Well, that's the thing. Moving forward, we're going to use lowercase d for something else.
Oh.
So, you know, basically what I'm getting at here is that in Calc, all the way through now, we have been using dy dx incorrectly because it means something completely different.
So it should have been this symbol the whole time?
It should have been this symbol the whole time.
Oh.
So, but, you know, like let's say you never get to this course, what do you know? What do you care, you know? So, but it isn't until this moment where it becomes relevant. Right? So when I say delta f delta x, I'm saying the partial derivative of f with respect to x. All right? Because what I could be doing is taking the partial derivative of f with respect to the other variable in the function y. I could also be taking the partial derivative of f with respect to some constant. You know, that's the thing. Like, what you're taking the derivative with respect to, it could be anything. Sometimes not even relevant to the function. Like, for example, I have a function here in terms of x and y. I could take the derivative of this with respect to t. And we've done that before. That's parametrics, right? We could parameterize it in terms of a new variable, right? So there's no limit to in what way you can differentiate. Because really, if you go back to the idea that slope is a rate of change, you could create a new rate of change. I mean, I could take the rate of change of your grade over time, right? I just take like what the change is over the number of days, right? Or does it make sense? I don't know, right? Maybe you want to divide it by the number of tests. Like if I want, like let's say you have 3 tests, all equally weighted. You could average them together, all right? That average is a rate, right? You're taking the rate of change of your test scores per unit of tests, all right? That's what a mean is, that's what an average is. But then I could take that rate and relate it to time and create what we called in Calc 1 related rates, all right? So I could differentiate with respect to whatever I want. So this notation is the all-encompassing notation that we use for any kind of derivative, no matter what the variable is, right? And we'll talk about next class what the lowercase d actually means, right? But all this is telling us to do is treat y as constant and differentiate with respect to x. All right, so we're going to treat y as constant. All right, there's multiple forms of partial derivatives. The two most popular are this one and also the lowercase f with a little subscript of x. That means the same thing. People like this one, I think for obvious reasons. It's less writing. All right, so just f with a little subscript of x. And then when you get into second order partials, which I should have, yeah. So here's a second order partial. For example, this is a mixed second order partial. First derivative with respect to x, second derivative with respect to y. You could write it like that, but if you use this notation, it's much simpler. All right, so we'll get to that in a minute. So, yeah, partial with respect to x. We do it a piece at a time. I'll color code. One thing I think that you'll probably like about this is that it takes functions that look like it's probably supposed to be product rule or quotient rule and makes it much simpler. All right, so 3x squared, my variable is x. So that's just, I take the derivative of that the way I normally would. So 6x. 4y squared.
Is that an F or a Y?
Is that an F?
Delta.
Oh, delta F. Yeah, it's supposed to be an F. Poor quality F. Because what's happening is when I take a derivative, or actually if I just have a function defined in terms of x and y, it's implied that that function represents z. You know, f of x was the same as y. F of x comma y is the same as z. All right, so this is really, I mean, if you were to use prime notation, you would think of this the way you would like y prime. This would be like z prime. All right, but z prime of what? Like, are we talking in terms of x or in terms of y? So we have to be more particular about our notation here. All right, now 4y squared. If we're treating y as constant, then 4y squared itself is constant. Derivative of a constant is equal to 0. That just got a whole lot nicer. This next piece, you don't have to do this step of rewriting it, but at least this one time, maybe you should. I'm going to rewrite it as negative 2y times x squared. All right, because y is constant, that makes the negative 2y into a constant multiple. Or a scalar multiple. So when we take the derivative using the power rule, we take the power, multiply it by the coefficient, reduce the power by 1. That y, I mean negative 2y, that might as well be negative 27. Or negative 200 if y was equal to 10. Whatever, it doesn't matter. You're treating it like you would if it were a coefficient. So 2 times negative 2y is going to be negative 4y. Reduce the power of x by 1. So times x to the first power. Do the same thing for the next piece. 7xy squared. We could think of that as 7y squared times x. That x has an understood power of 1. Power multiplied by coefficient. Because again, that's 7y squared. No matter how complicated it is, it only consists of coefficients multiplied by y's, which we're treating as constant. So no matter how complicated it is, it's still going to be treated as a constant. All right, so 1 times 7y squared is 7y squared times x to the 0th power, which would go to 1 anyway. And that last little negative 9 there, irrelevant, because the derivative of a standalone constant is going to be 0 anyway. So we're looking at 6x minus 4xy plus 7y squared. All right. Now in Calc 1, the way you would have handled that, you would have had to use implicit differentiation and product rule. That would have been crazy. Mechanically, this is not bad, right? It's just not something that you're overly eager to do, but it could be a lot worse. Oh, speaking of worse, compute all 4 second-order partial derivatives. All right. So what I'm going to do is snag my previous answer. So partial with respect to x was 6x minus, what was it, 4, was it 4xy plus 7y squared? All right. It's when you get into second order partials where you're like, yeah, let's talk about that other notation right quick. So we could look at this as just an f sub x, because if I want the second order partial fxx, fxy, we need them both. All right, because all 4 would be partial with respect to x, then y, x, then x, y, then x, and y, then y. All right, so we have all those permutations that we have to account for. All right, and you can do it in any order you want. I tend to want to do the mixed because they're actually, I'm going to steal my own thunder a little bit. There is a relationship between mixed higher order partial derivatives. So if your function is continuous, then your mixed partials will be equivalent, right? So your f of x y would be the same as f of y x, right? So, but that's only if it's continuous, which is why we were talking about continuity, right? So you just have to keep in mind what it is you're looking for here. So I'm working off of my first order partial with respect to x. Now I'm going to take its derivative with respect to y. All right, so my variable here is y. So I'm going to highlight the relevant variable. Everything else is treated as constant. So the derivative of 6x goes to 0, irrelevant. The derivative of this, that y, has an understood exponent of 1. That is, again, a highlighter and not a marker. Power multiplied by coefficient. My coefficient now is negative 4x. So 1 times negative 4x is negative 4x. Y to the 0th power. Okay, well, y to the 0th is 1, so ignore it. This, I'm taking the derivative. Again, my relevant variable is y. So I'm taking the derivative of this with respect to y. So I'm going back to Calc 1 and taking this derivative. All right, so 14y. All right. Going back to my first order partial, I take the derivative now with respect to x. So 6x goes to 6. That's easy enough. All right, my relevant variables are the x's. That 7y squared is going away because there are no x's in there. So 7y squared is constant. So now it's really just a matter of accounting for this middle one, which could be thought of. All right, so I'll just circle it, pull it off on the side. That's the same as saying negative 4y times x to the first. All right, so power multiplied by coefficient minus 4y. X to the 0th power, drop it because x to the 0th power is equal to 1. All right, so now we got to do all that again, but this time we're starting off with a first order partial with respect to y. Skill-wise, it's going to be exactly the same, though.
Question. Don't we have to do a f of yx? Or we just come to that?
Yeah, that's what we're going to do in a minute, yeah. All right, so now what we're looking at is going back to the original function and differentiating that with respect to y. So my relevant variable is y. Every instance of x is going to be considered constant. So 3y squared, done. I'm sorry, 3x squared. All right, that's constant. Derivative of a constant is equal to 0. 4y squared, take the derivative of that Calc 1 style, 8y. This could be thought of as negative 2x squared y to the first power. Power by coefficient, reduce the power by 1, negative 2x squared. Same idea for the next one, except the power is 2. So plus 14xy. So now I want to do, I personally, again, like to do my mixed second order partials. All right, because these functions are continuous. I know they're continuous because I don't have any radicals. I don't have any denominators with variables in it. I don't have natural logs. I don't have trig functions. I don't have anything that would cause any funky values here. So I expect this mixed second order partial to be the same as that one. All right. So I'm differentiating with respect to x, which means that the 8y is constant, goes away. This one becomes negative 4x. And if I think of this as 14yx, that would differentiate down to 14y. All right, so it verifies what I was saying. I mean, maybe not the continuity part of it, but at least that the second order partials would be the same. So, you know, you kind of look at a situation where maybe you have a fourth order partial that has two x's and two y's in it. It doesn't matter what the arrangement is. All right, so let's say it's a fourth order partial. So the fourth derivative, and in one case it says you're supposed to do f sub xy xy, and in another case it says f sub yy xx. All right, they're both mixed fourth order partials because the functions, I'm establishing that the original functions are continuous. Those two mixed fourth order partials should be equivalent to one another, which means pick the easiest pathway to get you to that arrangement of partials and you're good to go. All right. For here we go back to f sub y. So 8y becomes 8. We don't expect this to be the same as f sub xx, so all bets are off here. But nicely, the negative 2x squared is going to go away. And we'll be just looking at 14x. All right, so plus 14x. All right. So numbers 3 and 4 are basically a rehash of 1 and 2, except there's some trig and exponentials in there. So again, my teacherly right.
This is compute all four second order, and we got 6 of it.
1, 2, 3, 4. These are first order partials. But we needed to get the first order partials in order to get the second order partials. So, yeah. So there's a lot of writing, and these will take you a few minutes, but it's definitely worth your time because there is a little bit of quirkiness when it comes to transcendental functions, the exponentials and trig, that is worth spending some time on it. All right. So that'll do it. If you have any questions, stick around. Otherwise, have a wonderful evening, and I'll see you on Wednesday.
Yeah, I did see my average.
Right.
I was surprised.
Yeah, so, I mean, you're in the
Yeah.
game, that's the whole thing.
So, yeah, I just got to hit the two exams.
Right. And let's see, like you could do some typos. That'll get you up a little bit more.
But yeah, I've always been doing those.
Yeah, you've been doing a tech
bonus
assignment, so yeah, it's gonna just cut it, like if you get that average up
Yeah.
a little bit.
stuff. Okay.
Yeah, you're gonna, like,
Exactly.
it's
So
still
the next-
doable, yeah.
'cause we have another test in the final, right?
Yeah,
Okay, cool.
Do I have hope?
yeah, absolutely. Yeah, because what are we at here? Like,
Going back on the phone, I was thinking of dropping this because not that I need it, but I just want to be
Yeah, yours are it's the tech assignments.
Yeah.
If you get, let me just
I
put
don't
it
have
in.
time. I work in Jersey City, 5 hours drive back.
Right,
It's like,
but,
and then I come here, it's like, I'm drained.
no, I
I'll do
understand.
them all.
Yeah, but let me just put it in perspective for you. If you get those in, you have like a B.
Oh, good.
Yeah, so I mean, it's very doable. Like, you know,
I wanted to get it higher, but it's like,
right, but
I
that's
understand
that's
the
a place to
topic.
start, you know?
I understand the topic, but it's memory that's like,
Yeah,
it's hard for me to, unless I write down every sheet of paper, then in one, I can't.
right.
Thanks.
Yeah, no problem.
I thought, weren't we supposed to have a quiz today?
Yeah, we were, but I forgot to make photocopies, so that ended up not happening. So I'm gonna reschedule that for next week.
Okay, cool.
So, but I'll talk about it on Wednesday, and then we'll do it next week.
Okay, that's right. I just was wondering about that. And
Yeah.
For the last quiz, for the bonus.
But it was a smart move not to bring it up like an hour ago. Yeah.
I just want to keep my mouth shut there.
Yeah,
For the last quiz, for the bonus, is it still possible if I may hand that in?
The last, the unit circle one?
Yeah.
Let me
get
s-
your time under, what, 2 minutes?
Oh, I said that to you.
2:30.
2:30.
Yeah, that's fine. Yeah, totally.
Where would
Yeah,
that
just-
show though?
Was that?
Where would that extra credit show?
It would be on Blackboard. It's under bonus unit circle game.
Okay.
Yeah, it's all up there.
Did you count this?
And yeah, you got credit for that.
Me?
Yeah.
Alright, because I remember sending it to you.
Yeah, you definitely got credit for that.
Would you count this as an error?
Did you back the test or?
Oh yeah, yours is like right there somewhere.
Okay.
There it is.
I know, just like.
Yeah, I didn't look so hot.
That, between the F and the parenthesis right there, could there be a space? or-
Yeah. I'll take anything that makes my notes better. Yeah, like I'm not picky. Like even if it's something like aesthetic, you know, like if it'll make it look nicer, if a suggestion, you know, I'll take anything. No problem.
I didn't do so hot on this one.
Yeah. So,
Yeah.
but your average is not terrible. So I mean,
Yeah.
even with that, to still be like living in the B territory is not like.
Yeah. But this one, if this is my lowest grade, this
Then
fits-
it would drop. Just watch attendance because you can come in late.
Actually, no, I don't really come in late. I usually come in on time. I usually come in like 5 minutes
half
late.
an hour
All right,
late
that's
today.
that's just for today. I always come in on time.
I got you 3 consecutive classes late.
Can I see how late was I? Because I remember you saying that I could come at least like 5 minutes late or 2 minutes, and I don't come that late. I know that for a fact. I don't do that.
Yeah, the problem is I wait before I take attendance. So if
That's
you're-
why I was shocked when I saw my participation as 5 out of 10.
Yeah, so just like just get that.
Because I know I come in on time. Like I come in within 2 minutes. Within like usually I come on exactly on time. But like I was so shocked when I saw that too because I know I come in on time. Like I don't come in that late. I know you gave me like there's like a 10-minute span or a 5-minute span.
Right.
And I always come in within that. Exception.
That's not the final grade for participation. So like if you could just maybe a minute earlier, 2 minutes. I mean today it's a different story, but
Yeah, today was I had something to do.
but like yeah, just a smidge earlier.
Yeah.
That'll be fine because that could easily. I mean, it goes. I revise that grade at the end of the
Oh,
semester.
really? Okay.
Yeah, it's not like that grade is the grade and then
Yeah.
I put a new one in. I change that grade at the end of the semester.
Okay.
So you could expect, as long as you get the attendance squared away, then you could expect that to go up. It could even become a perfect score.
Okay. And I can still apply for my lowest test grade to be dropped, right?
Yeah.
It's
That's why I always tell people to be mindful of attendance because if you go over that threshold, then you lose the ability to drop your lowest test grade, and that's more than participation score. That's the big deal.
Yeah. I don't want to lose that at all. 'Cause
Yeah.
This test was like, I don't know. I for sure I didn't want.
How's dropping your test grade work?
If you meet the attendance requirement, which is I gotta look it up because it changes from class to class, but usually it's 2
days absent.
Yeah. So 2 absences, two unexcused absences. As long as you don't go over that, then you can drop your lowest test grade.
Oh, take your pause.
You're welcome, but take it easy. So you're in good shape. So as long as you don't hit a stretch of absenteeism, you'll be fine. you know, so then that test can go away. And then, yeah, the only thing is the trade-off is that you'd be on the hook for the final exam. But, you know, like for a lot of folks, they hope to be able to take the 3 tests, have an average that they're happy with and not have to sit for the final. But, you know, like having the bailout of not having, you know, to have a bad grade count, that's the important thing too, you know.
I want to know that to get the limit does not exist for this one. This one has to not equal these two.
Correct. Either of them. Once you get one different limit, then you've showed
just
that the limit
doesn't
doesn't exist.
exist.
Exactly.
Have a good day, Professor.
You too, but take care. All right, so then we're on page 56. All right, so then partial derivatives, second order partials, all that good stuff. We'll learn about tangent planes tonight. All right, so number 3 is a pretty funky looking one. 4 is even funkier because it's asking for all 4 second order partial derivatives. But here it's just saying the partial with respect to y. All right. I suppose it didn't need to be a separate question because we got to do that anyway in order to answer number 4. But just to have a standalone question where we're just focusing on y, I think it's a good idea because it's kind of hard if you're not accustomed to this to think of something like cosine of x as a constant. We're treating it as constant. All right. So partial with respect to y. So this is a constant multiple. We're treating it as a constant multiple. All right, and so that would be the same for the other x. All right, the one that's in the power of e. All right, so what I'm going to do is I'm going to differentiate around the sine of x. I'm sorry, the cosine of x. So I'm going to leave that as part of my solution and then take the derivative of the other part in terms of y. So the derivative of sine is cosine, so we're going to have cosine of y. All right, it's with respect to y, so it's not like implicit differentiation where I need to slap on a dy dx. It's just going to be times cosine of y. Then minus, when I take the derivative of exponential e, that's not a highlighter. The technique is to rewrite as is, so e to the xy, multiplied by the derivative of the exponent. All right, my derivative of the derivative of the exponent, and I'll just kind of make a little note here. It's really saying d dy of just xy. So x is the constant multiple. We're treating it as if it were like a 2. All right, so yeah, you're right. It is going to be x. So I'm just going to pop that in there. But basically what we're doing, just as a quick justification for it, let me just make this look a little nicer. We're applying the power rule. All right, I'll just pop a power of 1 here. We're doing power multiplied by coefficient, reduce the power by 1. All right, because that x is taking on the role of a coefficient. All right, it's just some constant value. Now, for exponentials, we always multiply by the natural log of the base, so times ln of e. It's just when the base is e, it goes to 1 anyway. The reason I'm bringing this up is because I have the utmost confidence that you can all find the derivative of exponential base e. But if I throw an exponential base 2 at you, I have the utmost confidence that most people are going to forget to multiply by ln2. All right, so that's why I'm bringing it up here. It's always been there. It's just we never write it because it cancels out immediately. All right, ln of e is equal to 1. All right, but if this were 2 to the xy power, we would write 2 to the xy times x times the natural log of 2. All right, so just something, you know, old Calc 1 stuff that you should always be mindful of. And actually, I don't even know. I mean, it used to not be in Calc 1. Originally, it was the first part of Calc 2 was when you got into exponentials and logs. Then they changed Calc 2 completely, Calc 2 and Calc 3. They moved, sequences and series used to be in this course, they moved it to Calc 2. And in theory, exponentials and logs was supposed to be moved to Calc 1, but not everybody got that memo. So what happened was there was a whole cohort of students coming out of Calc 1, going through Calc 2, having never learned how to take the derivative of exponential or log functions. And then you get to me, and I'm like, well, of course you know the derivative of natural log is 1 over x. And they're like, whoa, when were you supposed to know that? You know, so if I'm slowing down and boring you with some of these rules, it's kind of for that reason, because I don't always have a whole heck of a lot of confidence. I was like, they're like, sorry, that's the faculty law. And I'm like, oh, sorry, I'm faculty. They're like, oh, really? I'm like, listen, I dress like a slob, I know, but I don't care. Yes, I am a teacher here. Well, how long have you been here? You must be new. I've been here for 20 years. And they're like, oh, you've been working here longer than I have. I'm like, yes, I have. Please leave me alone now. So, oh, I got stickers, I got everything. They just assumed that I was not doing the right thing. And the one thing I don't ever appreciate is when somebody is assuming that I'm not doing the right thing, but then they cop an attitude with me about it. Like, give me a chance to show that I'm doing the right thing first. And then if it turns out that I'm not, then it's like, sir, you can't park there. Like, first find out that I'm not supposed to be parking there before you give me that. That person blocked my car in. Like, I was walking out to my car. The security car blocked my car in because they thought that I wasn't supposed to be there. And I'm like, not only is there a sticker there, but I've been working here for 2 decades. Like,
Should have been like,
do you know who I am?
you should have been like, I go golfing with your supervisor, you know that?
Oh, that's a good one.
But they do that at night when you go home. They always stop people. They don't think they're students.
Yeah.
Even though I have a sticker now, they would just stop at, what are you guys, wacky or what?
Yeah, like, just, I understand there's like, there's bad eggs that cause problems for other people, but just don't assume that I'm causing trouble. When I'm causing trouble, you'll know. I'm not really in trouble. But I do sass people back when they give me a hard time. Yeah, second order partial. So we have a first order partial with respect to y. So I need a first order partial with respect to x, and then I need those 4 second order partials. So you can tell that I gave just the appropriate amount of space for you to do all this work. I gotta stop standing up, my knees are killing me. So I might as well start off with the y's, all right? So I'm just gonna clean up this one just a tiny smidge and write it as cosine x cosine y minus x e to the xy. Just a tiny little bit, just to make life a little bit easier. I'm also going to use the other notation, f sub y, because as fancy as the delta of f delta y is, and as cool as you feel writing it, it does get a little old having to write that over and over again, especially for the second order stuff. So f sub yy,
What happened to the natural log v?
ln of v is equal to 1.
Oh, right.
So that's going to cancel. All right, so when I'm taking my second order partial with respect to y, I'm basically doing the same thing that I did previously, just with my first derivative. So I'm going to hang on to the cosine of x. I'm going to take the derivative of cosine of y, which is negative sine of y. Now, for the second piece, it's actually not bad when we do it with respect to y. But if I had to do it with respect to x, it would be kind of problematic because one way that x is treated as a constant. The other way, it would be a variable, in which case you'd have to use product rule. Right? So in this case, it's not bad. So minus x as a constant multiple, rewrite e to the xy as is, multiplied by the derivative of the exponent. Right? So derivative of the exponent, again, is just like we did before, is just going to be x. And then the natural log multiplied by the natural log of the base, ln of e, which immediately, again, cancels out. All right? So we clean it up a little bit. At this point, it's really not necessary to because we're not doing anything. We don't need third order partials, at least until I get to the next page and find out that I'm completely wrong. I honestly don't remember. So minus x squared e to the xy. All right. So not terrible, but now I need f sub yx. All right. So f sub yx, taking the derivative with respect to x now. All right, and that spices things up a little bit. So that's telling me that I'm hanging on to the cosine of x. I'm sorry, cosine of y, because that's the constant multiplier. Then I'm going to take the derivative of cosine of x, which becomes negative sine of x. That's not the part that makes it spicy. It's this part over here. I now have to take the derivative of that using the product rule. Because x is the variable of interest, and what I'm looking at is the product of two functions, x and e to the xy. In the other context, when I was differentiating with respect to y, that x was treated as a constant multiplier. So yeah, it could have used product rule, but when I went to take the derivative of the constant, it would have gone to 0 anyway, right? So minus the first function, x, times the derivative of the second with respect to x. So e to the xy. So I'm treating y as a constant multiplier. So the derivative of, really I can think of that as yx is going to be y times ln of e, which again immediately cancels, plus the second function, e to the xy, times the derivative of the first, which is just a 1 anyway, right? Because it's, again, with respect to x. So changing your perspective is very, very critical here. Now, we talked about this very briefly last class, but it is a critically important relationship, and that is the idea of mixed second order partials. So I can show you again, but I don't think I need to, / I don't think you want me to. Last class we went through all 4 of the second order partials, including the mixed ones, and we determined that f sub xy and f sub yx were the same exact thing. So if your function and their derivatives are continuous, then your mixed higher order partials will all be equivalent. All right, so function and its derivatives continuous mixed higher order partials are the same. All right, terrible penmanship, I know, but it's saying the function and its derivatives are continuous, then the mixed higher order partials will be equal to one another. All right, so that's telling me that even though I just did all that work to figure out what f sub yx is, that's also going to be the same as f sub xy, which is hugely important, right? Because in order to figure out that last second order partial, I need my first order partial with respect to x, and then I just need it again with respect to x. All right, so that's an easier pathway than having to do pretty much everything I just did in order to just come up with the same answer. All right, so very, very important. Now, how do you assess continuity? Well, we spent time talking about that, but basically in a nutshell, it's talking about the idea that it's not going to be undefined or imaginary for any x value, right? So, or y value. So if I had an ln in here, all bets are off, all right? Because ln is not continuous for all values of x. All right, now if I have a restriction on my natural log function, all right, so if I'm not saying natural log from negative infinity to infinity, then it's fine, because I could make the restriction that I'm only looking at values of x that are greater than 0, right? But you can think of other situations. Throw in a radical, throw in a denominator with a variable in it. It tends to mess things up, right? So for the other second order partial, what I want to do again is go right back to scratch, which kind of sucks. Oh, I did have extra partials there for the same thing. Okay, well, it is what it is. I think that might be overkill. So my first order partial with respect to x, I'm holding the sine of y as constant, taking the derivative of cosine of x, which becomes negative sine of x, minus e to the xy, yeah, that's the derivative, times the derivative of my exponent with respect to x, so that's just a y, times the natural log of e, which again cancels immediately. We still need to find the second order partial with respect to x, so it's still part of 4. I'm just writing it up there for a space. All right. So you may have kind of thought about this and said, "Oh, do I have to keep writing that ln of e?" You never had to write it. I'm just writing it every time because I figure if I do that, then when it is something like 2 to the xy, you'll be in the habit of writing the ln part. All right. So it's something that I'm trying to do to kind of help you from making a careless error down the line. Bless you. All right, so now I need f sub xx. And that's the last thing I need. Because I don't need f sub xy because I already figured that out indirectly. So taking the derivative of this with respect to x, which means all my y's are constant multipliers. So sine y, hang on to that. Negative sine x has a derivative that's negative cosine of x. Now, that ye to the xy, when it was the mixed second order partial, then it was a product rule situation. But now it's not going to be like that because the y is treated as a constant multiple. So much simpler. So minus y e to the xy times x, times y because it's differentiated with respect to x, times the natural log of e. Again, kills the ln of e immediately. So negative sine y cosine x minus y squared e to the xy. Phew, Jackman. Look at that. It's crazy. Look at all that work. And we still don't even know what this is used for. Right now it's just an exercise in just doing derivatives for the hell of it. We're going to see in a couple minutes what it's used for, though. And it's pure excitement.
So it's always good to do all four, then, just to get used to it.
Yeah.
To do the f of x, do the f of y, do the f xy, and the fyx.
Right, for at least for practice, but then, you know, like, once you get a feel for it, then you start saying, all right, if I need to get mixed second order partials, what's going to be my easier pathway? You know, that's the thing. So like, for example, in number 5, where I'm doing a third order partial, mixed partial, like I have to do f sub x, y, x. So I would look at everything that I did here for my my second order partials and decide, all right, well, which is going to be my easiest way, my easiest pathway to get where I need to go, right? So, because like this kind of question, I mean, yeah, it's building off of work that we already did, but imagine it's a standalone question on a test, right? You don't want to have to do all of this work just to figure that out. So what you would do is you'd say, okay, if I know that all mixed third order partials are going to be the same, then what's going to be my easiest way to get there? So f sub x, y, x, we know that that's going to be the same.
Oh, sorry, I didn't follow that. I mean, I don't understand what that symbol stands for. Is it saying it's the second order of the first one?
The second
order is y of x of f of x?
For this one?
Yeah.
This is saying first order partial with respect to x, second order partial with respect to y, third order partial back to an x. But this is going to be the same as f sub x, x, y, f sub y, x, x, f sub, I got x, y, x. So, what am I missing here? Y, no, there should only be one y. Do I have it all? No, I think I have it all, yeah. Okay, that's why I can't figure out another one. All right, so all three of these things are going to be the same, assuming, again, that your original function and its derivatives every step of the way. All right, so if I'm looking for a third partial, my second order partial needs to also be continuous. All right, continuity is the key to everything. All right, so I have 3 possible pathways to get to the required value that I want. So I could even look at this and then say, well, f sub x, x, y, y. You know, just change up the ordering of it because the different permutations still lead to the same outcome. All right, so I look at all of this work and I say, well, it doesn't matter because I already did it. But if I'm starting from scratch, I'm liking this one. I'm liking this one more than I'm liking the others. All right, because starting from scratch, I can take the derivative with respect to x, then take the derivative again with respect to x, and then it's only at this step that I would take the derivative with respect to y, right? which is going to be a lot easier. All right, so I'm going to pop a star on that because I got you going on it at least, and then let you play around with that. So we're going to talk tangent planes. Tangent planes are cool. You know, when you're talking about two-dimensional functions, you know, like a parabola or something like that, when we're talking in terms of rates of change and things along those lines, tangent lines, instantaneous rates of change, that seem to make sense. Okay, so a two-dimensional figure to assess a rate of change for another two-dimensional figure. So it would make sense that if we span up to 3 dimensions, now what we would be doing is looking for a 3-dimensional way of representing that rate of change, right? Because, yeah, like you're walking up a hill, right? So it doesn't matter how steep it is. I mean, let me just put it to you this way. If you're going hiking, you could make it as steep as you want, right? So Breakneck Mountain, I don't know if you're familiar with that. I don't go hiking a lot, but I like Breakneck because like they had the easy trail, and then they have like the more challenging trail, and then you could just climb up the cliff face if you want. You know, like you could go nuts with it. But basically the path that you take dictates the rate of change that you're going to experience along your route, right? So if I want to go a zigzag approach, my slope, my gradient, if you will, we'll get there, is going to be not as steep as the person's going up the cliff face, right? So it really does depend on the direction in which you're going up or approaching a particular point, right? So a tangent plane helps us do that because it's an omnidirectional way of representing a rate of change. Because if I have a plane that's going to be tangent to a point, then I can move along that plane any way I want and still get a sense of the rate of change, all right? We are going to learn about gradients. Gradients, again, is just a 3-dimensional way of representing slope. Actually, it's not just limited to 3 dimension, but that's what we're going to focus on. The term slope is actually just the 2-dimensional way of thinking about gradient, right? Because really, if you're talking about, like I said, climbing up a hill, walking up a hill, the slope is just, you know, take a cross section, take a knife and just slice right down vertically down the hill, and then just map out that pathway that is the intersection of that cut and the hill, you know, that cross section, just the perimeter of it. That's your 2-dimensional rendering. The tangent line, instantaneous rates of change, the secant line, all that stuff, all that's doing is just focusing on just that one possible pathway. We want to be able to focus on any possible pathway. So what I used to do in this course was actually derive the tangent plane approach, and it in and of itself took up like a whole class session. So what I did was I took idea along with, you know, learning and stuff, but one thing at a time. All right, so rules. We got rules. Plenty of rules. Suppose that f(x, y) is continuous first order partial, so continuous continuity is hugely important. So why do we spend time on domain and continuity? Because of that. Normal vector to the tangent plane at z at AB is going to give us this relationship. And so you got to be really careful, and people easily lose sight of this. If I were you, I'd make a note. These are first order partials, right? Because people look at this, and no matter how many times they look at it, all they keep seeing is f of a comma b. All right, so what we're looking at here again is first order partials. That's the one drawback to this kind of notation. Because up until this moment, f of x, f of y, always just meant plug those values in and call it a day. This is the first order partial with respect to x, so I'm taking the derivative with respect to x and also with respect to y, and then putting in my AB value. All right, so that's a normal vector, those values, and then a -1, right? Most people look at it as like, whoa, that -1, where is that coming from? It actually comes from the solution to a reduced row echelon technique, so row reduction, RREF that we did in our calculators. So that part of the solution bears itself out, and there is a reason for it, but that's something that you would look at the activity for. Further, an equation of tangent plane is given by this. All right, so you see here we have just that naked f. All right, that's the original function with evaluated for a and b. All right, so you have the recipe for the tangent plane. It's very easy. But again, if you want to know where all this stuff is coming from, then you go to the activity that I'm posting in a little bit. The equation of a normal line through the point is given by these functions, right? So, but that's really not what the first part of the question is asking. So we'll focus on tangent planes first, all right? So this looks like an overwhelmingly difficult question because I gave you 4 coordinates, which means we have to come up with 4 different tangent plane equations. This is going to take us the rest of the night. Actually, it's super easy, barely an inconvenience. It's going to take like 5 minutes maybe, because these points are hand-picked because they're actually very convenient. All right, so first what I need is my function. It says z equals. How about f of x comma y instead of the z? So then when I'm looking for my first order partial with respect to x, I'm treating y squared as constant multiple. So I'll just put that down first and then multiply by the derivative of the x component. So just a 2x. Clean that up ever so slightly and you get 2xy squared. All right. We'll worry about our partials first and then we'll tackle the coordinates. All right, the second partial that I need, first order partial with respect to y, I hold the x squared as constant and then take the derivative of the y squared term, which is going to give me a times 2y. And so what I'm looking at here is 2yx squared. All right, so compare this to what we did with that sine cosine function with the e in it. Much easier, right? They're not always going to be crazy difficult. The one went away because it's constant. We didn't have to treat it as constant. It already was constant, right? So now I want to tackle my tangent planes. So at 1, 1, I'm going to find my different components. All right, so I need f of 1, 1, first order partial with respect to x at 1, 1, first order partial with respect to y at 1, 1. All right, so very easy calculations. Plugging in a 1 for x and a 1 for y. So 1 squared times 1 squared is 1, plus 1 is 2. So I got that bad boy. Two times 1 squared, 2. 2 times 1 squared, 2. So all these calculations were very easy. And so my tangent plane,
Isn't f 3?
is it 3?
Because it's 1 squared plus 1 times 1 squared.
The 1 squared.
Oh wait, I'm an
Yeah. Oh, not yeah, and it's 2, not yeah that you're an idiot. So, be clear about that. So z equals f of a comma b, f of 1 comma 1, which is 2, plus first order partial with respect to x of 1, 1, which is 2, times x minus a, the a value is 1, plus my first order partial with respect to y, add 1, 1, which is 2, times x minus the b value, which is also 1. And that's the equation of the tangent plane. So what that means is that if I plot the point at 1, 1, now remember, this is a three-dimensional surface. All right, so 1 is the x, 1 is the y. The z value is 2. So the coordinates are 1, 1, 2. This is the equation of the plane that would just touch the surface at that point. All right. Now, it doesn't look like our plane equation, which is normally ax plus by plus cz equals d. But if you clean this up and simplify, that's what it would be. All right. So when we talk about that vector, that f of a comma b, first order partial with respect to x, first order partial with respect to y, both at a, b, and then -1, that's coming from the solution, because if I brought the z over to the other side, it would become -1z. So the coefficient of x, of y, of z make up your normal vector. And so coefficient of x is equal to the first order partial with respect to x. Coefficient of y, oh, this is supposed to be a y, is equal to the coefficient of y is the first order partial with respect to y, and the coefficient of z is always going to be that -1, because it's always in the form of z equals. So if I were to move it over, it's always going to be a -z. All right, but let me make this a y as it ought to be. And so you think to yourself, dang, I got to do that 3 more times? Well, yeah. So at 1, 0. So I need f of 1, 0. So I plug in a 1 for x, a 0 for y in my original function, and I'm going to get 1. Now, it seems harder than it is, because anytime I incorporate a 0, it's going to streamline things. So f sub x and f sub y both involve a product of x and y in some capacity. If I know one of them is going to be 0, doesn't matter if it's the x or y, both of these partials are going to 0 out. Which means, just looking back at this, yeah, z equals 1. 0, 1 is going to be the same thing. Yeah, same thing. Because we know that the partials are going to 0 out. And if you plug in a 0 for x and a 1 for y, it still simplifies down to just give you a 1. All right? So that happened a lot quicker than you might have expected going in. At 0, 0. Well, we know the first order partials are going to 0 out. It's just a matter of what the original function is going to be equal to when x and y are both equal to 0. Still 1. So really not difficult at all. Now, the second one, a little bit of a different story. Because we have a cosine function containing both the x and the y, so when I'm looking for my partials with respect to x, it is going to involve some chain rule. All right. The function itself, it's an interesting looking function. I mean, you look at the graph and you say, wow, that's pretty cool. That's like you drop a pebble in a pond. Calm water, you drop the pebble, and then it creates that rippling effect. Yeah, well, now you know what function would create that model, so that's kind of cool. All right, but it's still the same structure. So I have my original function f of x comma y which is equal to the cosine of, I'm going to write it as x squared plus y squared to the 1/2 power. Not for evaluating that function, but just to make life a little bit easier when I find the derivative. So first order partial with respect to x, keep it at, you know, the inner function as is. Derivative of cosine is negative sine of all that stuff on the inside. But then I need the derivative of all that stuff on the inside, which is going to be 1/2 x squared plus y squared to the negative 1/2 times the derivative of the innermost part of that function. All right, this is with respect to x, so the y squared is going to go away, so I'm just going to be left with a 2x. Now, worth it to clean it up? I don't know about that, not yet anyway. So let's just leave it as is until we have a reason to go further. All right, so f sub y, same. Really, it's the same exact thing right up until the very last step. Because the only part where we're actually actively taking the derivative of something involving either an x or a y was the part where we were taking the derivative of the x squared plus y squared. Right? Everything else would pan out the same way. So I need the equation of tangent plane and tangent line to the surface at these points. All right. So, oh, that reminds me, I forgot the normal line in the last one. Honestly, it doesn't really bring anything to the party. I'll take it as a typo. Because really it's the tangent plane stuff that I care about for now. So at pi 0 is my first point of interest. So f of pi comma 0 so I'm plugging in a pi for x and a 0 for y. So I just play this out logically. If I take the pi and square it, and then raise that pi squared to the 1/2 power, the 1/2 is going to cancel the power of 2. So it's really just asking for the cosine of pi, which is -1. All right. You know, you could pop it in your calculator, but I feel like, you know, just taking a second to logically reason it out, I think that pays off a little bit quicker for you. All right. So for f of f sub x, now here's where the payoff really happens. Because if you're always defaulting to going to the calculator, and you know me, I'm calculator all day, every day. But if you're defaulting to that, then you're missing out on an opportunity to find some shortcuts, right? Because we know that the inner function here for pi 0 is going to go to pi. What is the sine of pi? 0, which means all of this is zeroing out. All right. So much easier to do it that way than even typing it into the calculator. All right. First order partial with respect to y is the same ingredients. So if it's zeroed out for a first order partial with respect to x, then why wouldn't it do the same thing for y? So that's going to zero out also. And after all of that, we get the tangent plane at z equals -1. All right.
Sweet.
Now we do the same thing at 0, 0. But there's no reason to think it's gonna play out any differently, because whether it's the sine of 0 or the sine of pi, you're still on the x-axis, unit circle. On the x-axis, the sine function is always equal to 0. All right, so f sub 0, 0. All right, so plug in a 0 here, you're looking for the cosine of 0,
1.
which is a 1. And my first order partials with respect to x and y are both going to be equal to 0, because in either case, I'm taking 0, squaring it, square rooting it, whatever, but the sine of 0 is equal to 0. And so we're going to get the tangent plane being equal, or giving us a tangent plane where z is equal to just a positive 1. All right. So we got a lot of negative ones, positive ones. There's only the one instance where we got something other than that. All right. So these tangent planes are of the horizontal variety. All right. So parallel to the xy plane. All right. So if the plane is in the form of z equals some constant value that we can call a, then plane is parallel to xy. All right. Most importantly, what that means is that you're looking at an extreme value. All right. So it's giving us extrema. Relative max, relative min. You know, you might have learned them as local max, local min, but it's the same thing. Just because if you had turning points in 2 dimensions, there had to be something that is consistent with turning points in 3-dimensional system. You can see the little hump there. There is a little peak to that mountain. What we just discovered was that that peak is happening on the plane z equals 1. All right. At pi, comma 0, which is one of these points along this ring here, it's kind of hard to see, but if I bring it in a little bit, this ring here would be the fold that represents the lowest points along that graph. All right. So you have a peak, and then it's bowing outward. Right. So so you have like the hill, and then you have the valley, but it's happening in every direction, so it's not as obvious. So you look at something like this, but it's also happening like this, in every possible direction. Right? But every one of those valleys is corresponding to a local minimum.
So it's
And
-1.
and that's happening at the plane z equals -1.
Is it negative or 1 because those are the extremes of cosine function?
Yeah, it's actually, as it turns out, yeah. And specifically because the amplitude of that cosine function is equal to 1. So if we had z equals 2 times the cosine of all of this, then our planes would have been z equals -2 and +2 for the extremes. Right? But basically what we are looking at here is a cosine function in 3 dimensions. Right? Because if you take that cosine wave and propagate it outward, but going in every direction, and then connect all of the peaks and all of the valleys, you'd end up with this surface. Right? Which is why we don't spend a whole heck of a lot of time trying to draw these things, because it's a nightmare. But we can still evaluate them. Now, a little notice here, what is the equation of a tangent plane at extrema? I just kind of gave it to you. It's z equals some constant value a, right? But as it's been turning out, if you know that the extreme value is occurring at AB, then it would be z equals f of AB. All right, but again, that's assuming that the extrema occurs at AB. So the next logical progression in all of this is making a determination of the A and B values that correspond to extrema, right? Because in these cases, we were given the extreme values. We were told 0, 0, and pi 0. But what if we're given a function and they don't tell us anything? They say there are some extreme values, find them. You know, that's a different story altogether. In order to be able to handle that different story, we need to learn about the chain rule for functions of several variables. Okay, because what we could be dealing with are nested functions where you have a function inside of a function inside of another function. Right? I find that tree diagrams, and you know, this is kind of the standard approach, but tree diagrams end up being the most useful way to keep your thoughts organized when it comes to stuff like this. Yeah, I didn't really buy that the first time I saw this concept. I kind of tried to just Ted Can my way through it, which is basically my way of saying, oh, I got it, I'll just do it my own way. And then it actually turned out that this is one of those situations where the prescribed way of doing it is actually, I think, the best way of doing it. Right? So we have a function z equals x squared e to the y, where x is equal to t squared minus 1, and y is equal to the sine of t. It's asking us for a derivative of z with respect to t. All right, so the rate of change in z corresponding to rates of change in t. All right, so we got to think about what that means, because there's multiple layers here. Because if I'm taking a derivative of this function, there's two ways to handle it. I could find the first order partial with respect to x, or I could find the first order partial with respect to y. I think group texts are like the bane of my existence now. Because it's like whatever is being communicated generally never applies to me, but that doesn't mean that I'm not going to get like 40 messages.
And it's like the same two people texting back and forth.
Generally. But now I know that one of my relatives is out front of another relative's house in Virginia. Cool. Got it. Yeah. So once I take the derivative, the first order partial with respect to x, I can then, well, I can go a couple of ways. Well, in this case, well, it's only in terms of t, so actually there's only one way I could go. I could take the first order, or the second order partial with respect to t. So that would be, now it's a function of one variable at this point, so I would say, but you can still use the partial derivative notation, but I would be looking at the derivative of x with respect to t. All right. Now, if I take the first order partial with respect to y, the next part of the process would be to take the partial derivative of y with respect to t. All right, all of that is going to amount, those two pathways are going to amount to the derivative of z, which again is just another way, z and f are interchangeable with respect to t. All right, now we are going to tackle some cases where, you know, the second, you know, the embedded equation could be a function of two variables itself, right? But these are the two different pathways that we could go in order to get to our result. All right. So what that gives me is a recipe, and really that's what's detailed here. The derivative of z with respect to t is the product of each element of the pathway. So partial with respect to x, partial of x with respect to t, and then the other pathway, so this is an OR situation, that's why a tree diagram is a reasonable way to go, because each pathway is a different possibility, right? So in probability, Now, I don't know how much experience anybody has with that, but probability and statistics, and means multiply. Generally, I'm oversimplifying, but or means add, right? So it's either this and this multiplied, or this and that. So this times this plus that times that. So from my vantage point, rules are rules. I mean, there's a time and place for them, but I don't find value in those rules because I could just kind of invent them on the fly. All right, so what I would do at this point is take a look at my ingredients and say, okay, well, these are the things I need. So my first order partial with respect to x is going to be 2x times e to the y, because e to the y we're treating as constant. All right, there's no x in the e to the y, so e itself is a number. So that's like saying 2 to the third. You know, well, what would that be? It's just a constant multiple. All right, so then the derivative of x with respect to t is going to be 2t. So I'm going to multiply these two together, and that's going to give me 4xt e to the y. The other pathway was partial with respect to y, which I'm going to hang on to the x squared and then take the derivative of e to the y, which would be e to the y times the natural log of e, which goes away immediately. And then the partial of y with respect to t, which is going to be cosine of t. Multiply those two things together. And, you know, it's going to look ugly, but we'll take it. We're going to have x squared e to the y cosine of t. Add those two together, and that's your derivative. That's your derivative of z with respect to t. Oh. Poor people get too confused. That is a typo. Those should be partials. All right, so this is my blueprint for helping me find my derivative, but this is me actually carrying it out. So you see I found each piece, multiplied them together, and then took the two scenarios and their results and added them together. All right. The next example is a little bit more elaborate because you could see x and y are both functions of s and t separately. All right, so here the tree diagram is going to be the more important. And there it is. So partial z with respect to s is really what I'm looking for first. All right, that's my first job. But really what I'm going to do is I'm just going to use my notation and detail out every possible thing I could take a derivative of. And then in order to find the partial with respect to s, I'm just going to take the relevant pieces from the pathways that emerge. All right, so I'm starting off with my original function f. I could take the partial of f with respect to x, or I could take the partial of f with respect to y. But then when I take the partials with respect to x, the partial of x, I could do that with respect to s or t. I do the same thing for the y's, again with the idea that I could take the partials with respect to both s and t. So partial y with respect to s, partial y with respect to t. I apologize. Sometimes my my deltas somehow magically start turning into 2s. They should really start, I mean, they should, if anything, look like backwards 6s. Some kind of bug virus. Right, so this is what I'm looking for, ultimately. And these are all the different ways I could take a derivative from the information that was given. So what I want to do is I just want to go through this and identify any pathway that's going to get me to a partial s as a result. So starting with my original function, I could take the partial with respect to x and then multiply that by the partial with respect to s, partial of x with respect to s. Or I could follow this other pathway and ultimately end up with an s. So these are the relevant pathways. So starting with this guy, following this branch, or I can go with this guy and follow this branch. But ultimately, it's telling me the things that I need in order to find partial z with respect to s. All right. Now, ultimately, I also have to find the partial with respect to t, so I'm going to have to find all this stuff anyway in order to answer this question. But if I just needed that one thing, that's all the information I would need. Now, sometimes easier said than done because my f function looks a little on the funky side. Oh, okay. No, I thought it was a hand. So, looking at my original function, I could work with it as is, or I could clean it up a little bit. Cleaning it up would be like finding a common denominator and simplifying. You could do that, but you're still going to have a radical in there. So, like, why kill yourself trying to do something like that? I mean, if it ended up being something that you knew was going to clean up just with a little bit of perseverance, then that would be a different story. But that's really not how it's going to play out. All right.
Sorry, just to answer the first question, yes, you could either go to the left leaf or to the right side.
Right.
Either or.
Either or, but or means add the two. So it's like the mathematical or, which means you got to do both and add the results together. So it's unfortunate, but or makes it seem like you have a choice.
Yeah, I thought that's what it.
Yeah, probability, math, or means that you have to account for basically anything that satisfies the rule. So my original f, I could write it as, I'm going to make a slight adjustment to it, 1/4 x squared plus y squared to the 1/2 power. Nothing too crazy, just making it a little bit more power rule friendly. So that when I find my first order partial with respect to x, I'm looking at 1/2, 1/4 x squared plus y squared to the negative 1/2 times the derivative on the inside, which is just going to be 2/4 x to the first, so just 1/2 x. The y squared goes away because it's irrelevant. It's a constant, so constants go to 0. All right, and so we could clean that up a little bit, but we'll take the wait and see approach because I also have to find partial x with respect to s. All right, so 2t acts as a constant multiple, so I'm going to leave that in there, 2t. Then I just have to find the derivative with respect to s of cosine s, which is negative sine of s. All right. Then on top of all that, I have to find partial f with respect to y. Now that's going to have the same ingredients, except it's going to have a 2y at the end. So that's kind of nice. You can just kind of go into autopilot a little bit. partial y with respect to s, taking my y function, t is a constant multiplier, sine of s has the derivative of cosine of s, so t times cosine of s. So what I need to do now is really what I did before, it's just it's a little beefier. I got to multiply together and then add the results. All right, and you kind of pick and choose, you know, like, do I need to simplify? Do I need to cancel? Or there's some things I can combine a little easier? You know, like, for example, I know that I have to multiply all of this by all of this, so why not get rid of the 2 with a 1/2? All right. I know that this is a negative exponent, so why not make it the bottom of a fraction and put it back in radical form? You know, a little simplifying on the fly kind of makes this less of a painful experience. Less of a painful experience. It's still going to be painful. There's no way around it. But like anything you could do to kind of streamline it is going to make your life a little bit more manageable. So I have a negative, I have a t, an x, and a sine of x. Sine of s, I mean. So negative x t sine of s, and I'll just chuck that 2 in the bottom of the fraction. And honestly, I do that just so I don't have to rewrite all of this stuff again with just like a multiplication symbol in between. Right? It's a little bit more fulfilling. The other one, same deal. The 2 and the 1/2 can go away. We're going to have a denominator of 1/4 x squared plus y squared under a radical. And then everything else is going on the top, so y t cosine of s. And I'll just kind of move that plus sign into a place that's a little bit more visually appealing. So those two together give you the derivative of z with respect to s.
What information does this give you?
What's that?
Like, what would this tell you?
Oh, it's the rate of change of your z function per unit of change in s, but without knowing what x, y's, s, and t's represent, contextually it's not really telling much of anything just yet. But we're going to learn about, you know, the extensions of all this stuff. All right, so I put a little star on partial z with respect to t, because really it's just following the other branches. So I'd have to find, we did this part already, but I need partial x with respect to t, partial y with respect to t, and then those products put all together. All right, so put a star on that one so you can talk from that on here. All right, so with the last couple of minutes, I just wanted to talk to you a little bit about directional derivative. It's pretty painless. So, I mean, there's objectives and all that stuff there, but you have like a little bit of a contextual component here. And so this is kind of what we're leading towards. So being able to find derivatives allows us to be able to combine the concepts that we learned with vectors and also this multivariable stuff. All right, so function f of x comma y is the height of a mountain range at each point where x is equal to x comma y. If you stand at some point x equals a, the slope of the ground in front of you will depend on the direction in which you're facing. That's what I was talking about before. All right, so you're walking up Breakneck Mountain, you're taking the easy path or you're going up the cliff. You know, so the path that you're taking will impact the gradient. All right, it might slope steeply up in one direction, be relatively flat in another, and slope steeply down in yet another direction. The partial derivatives of f will give a slope, partial f with respect to x in the positive x direction. All right, we can also do the same thing in the positive y direction. but we can generalize this to give us a slope in any direction. That's what the directional derivative tells us. This is the limit definition of that, and I promised you that I wouldn't bore you with that, but this is really what we're after here. So this is gonna start the process of contextualizing this stuff so that we could actually make some good use of it. Now, you can see that the key components here are just simply finding partials with respect to x and y. All right, but it's also incorporating a unit vector, so that's coming into play also. All right, so I'll just do the first example and then I'll let you go, but it's easy enough so that you can start to get a handle on it. So partial with respect to x is just going to be 2x. Partial with respect to y is just going to be 2y. If I want the partial with respect to x at 2, 1, the relevant value to plug in would be the 2. I'm going to get a result of 4. Partial with respect to y at 2, 1, the relevant value to plug in is the 1, giving me a result of 2. All right. So what I need now is my unit vector. All right. So my unit vector comes from the given angle. All right. All related to the unit circle again. So the unit vector is going to be cosine theta, comma sine theta. In this case, we're talking about pi over 4. So in this case, we're looking at cosine of pi over 4, which is rad 2 over 2. Sine pi over 4, also rad 2 over 2. And so my directional derivative, d sub u, at 2, 1, is going to be the dot product between those partials and my unit vector, right? So if we're looking at f sub x, comma, f sub y, and my unit vector, u sub 1 and u sub 2, the directional derivative is the dot product between those two quantities, all right? So really all that means is just you're going to multiply your x components together. So 4 times rad 2 over 2 plus 2 times rad 2 over 2, which simplifies 2 rad 2 plus rad 2 to give you 3 rad 2. All right, so that's going to give us, based on this angle, the rate of change in our two variables. All right, so we'll talk about this a little bit more next class, but we restricted it down based off of the angle. But if I wanted to not make that restriction, if I want to have a function that would tell me what my rate of change or my steepness is for any value of theta, then we could leave it in general terms and work off of there. So we can create functions out of this, and that function would be known as the gradient. All right, so there's more to it, but that's enough to kind of whet your appetite, I think, a little bit. All right, so I'm going to put a star on number 2 so you can at least practice with that skill, and then we'll pick up with this next class.